Let's get started on chapter 2 is where we begin. So this is 2.1, rates of change and tangent lines to curves and kind of how they're related. So first we want to look at the concept of a rate of change. So rate of change, first one we want to look at is something like this: average speed. So if you're traveling in a car, which most of us do at some point or another, then you speed up, slow down, you get around the trucks and all that. Picture yourself going to Vegas or something. And when you're doing that, what you're doing is you have basically you can figure out an average speed it took you to get there. So it's supposed to. Oops, that was supposed to be time. So there's time t, and we'll call this s, often used for distance. So you start off at 0, so you're not going, and then you speed up. You get on the freeway, and you have to slow down on the traffic, and then you speed up again, and then it goes up and down all like that. So we can then take two time periods. Let's just say between, right here, call that T1, and then we go to T2 here. So you go up to the graph, and then that would be the speed here, and up to the graph here, and that would be your speed here. So you end up having two different speeds here. This is S2, and then this would be maybe let's see, that's S1, sorry. That's S1, and this is S2. And you can look at then the difference and look at the average rate between those two. Okay, all right. So now getting into the calculus, you can get the exact average rate, but this is just a rough idea or concept. So what you're looking at then is distance you travel, right? So it's however many miles to where you're going, divided by the time it takes you, divided by time. Miles per hour, meters per second, that is a rate. All right, so we've all seen that. So you have miles per hour, meters per second, right? The P is the per, M over H between miles and hours. What we see are meters per second, kilometers per hour, that kind of thing. So this is basically how we're going to define a rate of change. So let's see. Let f of t denote, right? So you're letting it be, or really it's a notation for, so you denote distance traveled at time t. Okay, so that's your distance. So s is basically f of t. So we can call this up here f of t if you'd like. So then if we want to look at average speed, average speed over some interval, so your interval then is T1 to T2, that's going to be equal to the distance traveled distance traveled divided by elapsed time. So the distance traveled is the difference of the function value. So come down here and say equals. Let's go and put in the division bar, make it easier on us. So that is your f of t2. So that's basically referring to this, let's change colors, this distance here. So that difference, so up here, this difference here is f, the top, so f of t minus f of t1, divided by the time elapsed is the difference of t2 and t1, t2 minus t1. And then we can use the delta notation. So anytime you do a difference like that, you can use the delta. So it's delta f of t divided by delta t. Or if you use the y notation, that's your delta y over your delta t, which you may remember is slope. That's slope of a line, change in y over change in x, or in this case t. So what you have then, oh, and then this statement, just to be clear, this is one statement. It's average speed over the interval is equal to that. So it's not like the interval equals that. It's the average speed over that interval. So what you want to be able to visualize then is this type of graph. So let's do another coordinate system. So you'll want to have, while you're taking notes, a straight edge to follow along and do all this. And you can pause and you know, get caught up when you're drawing all these pictures. So we'll draw a lot of pictures, a lot of graphs of what to do. So this is what I refer to as a generic style graph. So draw in basically with some sort of curve. So it could be doing something out here, and then you have some curve like that, suppose. I think that's probably good enough. And then here's x2. So this is going to go up to the graph here, up to the graph here. And then you have a line between those 2 points. That ends up being slope of that secant line. Okay, so there's my line, and then let's put in a few more points here. Let me zoom in a little bit there. So when we go up to the graph here, up to the graph here, and then you have this distance is your delta x, and then this distance is your delta y, the difference of. We often use q for a point on the graph. This would be your x2, f of x2. This point here would be, I'll call it, not q, sorry, p. So p and q, capital. So capital P of x1, f of x1 is the point on the graph. So those are all notations we might use. This is your function f. And so we call this line a secant line, right, between those 2 points. Okay, and so that's what you're getting here, right? You're getting that let's look at this guy here. You just replace x with that, and you're getting the slope of that secant line. Okay, so that is what's considered your average speed. If it's a distance, it's average speed. So you can call an average rate of change of the function. All right, so then keep in mind a couple other things to write. So delta x is defined to be the x2 minus x1. If we call that h, then you can rewrite that as x2 equal to x1 plus h. Or you can use that notation later. So I'll show you basically a way to eliminate x2. So keep that in mind as I show you this. I'm going to do a quick erase here. Okay, so this is the actual definition of the average rate of change. So what I was referring to back here was just speed, so you can visualize, something tangible, like you're actually traveling. That's your average speed, but does not have to be about distance. It could be a change in anything. So the average rate of change of a function y equal to f of x, and then I'll write this out this time, with respect to, and we'll abbreviate that WRT x, so I'll use this in the future when I say with respect to, over the interval and then your interval is x1 to x2, right? So it's this interval we're referring to from here to here. Is defined to be, and it's really the same as above, but we're going to start with delta y over delta x equal to f of x2 minus f of x1 divided by x2 minus x1. And then now we can change the notation a bit. If we replace x2 with what I have above here, then it becomes the other way of writing it. So it's f of x1 plus h, or plus a little bit, is how I want you to think about it, minus f of x1 all over, and then what does that denominator x2 minus x1 become? And that becomes your h. Okay, so we need to know both ways of writing average rate of change of a function. And so this is the slope of a secant line. So you want to keep that in mind as well. That's the slope of a secant line. Okay. So let's look at an example. Don't want green yet. Let's change that to my standard color here. Okay, so this is example. This is number 2 on page 43 in 2.1. And I won't always do that, but this one happens to be that question. And we'll do this one here, but then what I'll be doing is the problem sessions to have us work on more problems. So the question is, and I hate to rewrite this again, but the question is, find the average rate of change of the function over the given interval. Okay, so that's the statement, and it gives you, I'll come in and paste this later because I want you to work on it. So g of x is equal to x2 minus 2x, and the intervals that are given are 1, 3, and b, negative 2, 4. So the directions are find the rate of change of the function over the given interval. So that's this definition here. This is exactly what the rate of change is. So all we have to do is essentially substitute 1 and 3 into, well, for a, into that function. We wouldn't be using this one, right? Because we are not given h. We're given x1 and x2. So you just substitute into here and solve. So pause this and try that question. And then I'll take the question a little further because I just have to do that. So go in and pause it, but then you'll get delta y over delta x. And then so always write out your formulas if you have any. If you're so if we have a nice formula, then write it out, which is always a good thing. We don't always have nice formulas to write out. So substitute that into your function. So you get, what I like to do too sometimes is go in and kind of label. So you'd say, let's call this guy x1 and x2. So you're picking the right ones, right? X. So you're not saying, it's the subscript you're going to start using a lot more of. So when you substitute in, you get 3. So let me write this out. So big long division bar. You're going to get 3 squared minus 2 times 3. That's the first one. Minus bracket 1 squared minus 2 times 1 bracket. And then over 3 minus 1. So simplify all that. And I'll write some of it out this time. That's 9 minus 6 plus 1. So second part is just 1. So that's just going to be equal to 4 over 2 is equal to 2. So this is 9, and then that's 6. So that's that part. And this is just a negative, and then that is -1. So it gets you. So I did that kind of earlier in my head. So that's A. Try B, but I do want to talk about this function a little bit since we have it here. So let's graph that and talk about vertex formula, and things like that. So things that we're going to be doing, you need to know. G of x can be written as x times x minus 2. We could complete the square to get the vertex form or the graphing form. We know the roots of this thing are 0 and 2, and they're all single powers, so their multiplicity is 1, so it passes through those roots. Remember all that stuff? And then we can just use straight up the vertex formula. That one's actually nice to know. So the vertex formula, what is it? What's your A, or your x value? So it's minus b over 2a. And then you just evaluate at that point, minus b over 2a. So if we calculate that, our vertex ends up being, so your a is 1, where is it? So you're not using this form, right? You want to use this form. So, and I don't know why that's there. Okay. So when you calculate this, you're going to get negative 2 over 2 times 1. Okay, so that's equals 1. And I didn't want to put parentheses on that either. Okay, so your first coordinate is 1, and then you just calculate f of 1, which ends up being -1. So the vertex is 1, -1. So if you were to graph this thing, again, try it, pause it, and graph this thing, we get this. So I'll call that 0, and then we'll do 1, 2, 3, 4. And might have to change the scale a little bit, but so this scale, this would be your 1, -1, if this is -1 here. And it's, what type of graph is this? Okay, that's going to be a parabola, right? And you get, where was our intercepts 0 and 2. So here's 2. So your graph is going to go, here's your vertex, going to go something like this. Now I want to get a couple more points. So here's 2, you'd be up 1, 2, 3, 4. It's going to come like that. And then from there over 1, 2, up 1, 2, 3, 4. I only know that because the coefficients are 1, so it basically looks like this and like this. And it comes down and goes up. Wait, this part was wrong. So it's at 2, you're at 0. Then if you're over at 1, so 3, you're going to be up here. So you may want to get a point for that if you're going to do this nicely. So here's 3. So let's just do g of 3 is going to be 9 minus 2 times 3. So it's going to be 9 minus 6. I get 3. So you're up at 1, 2, 3. Well, it looks about right. I just wanted to sketch this, but then I made it into more of a problem. Okay, so it's looking like that. And so the slope then, when you go through 3, weren't those the points? 1, 3. So here's 1, 3. So here's 1 right here. And then here's 3, goes through here. So then you're getting this secant line right through here. Like that. And the slope is supposed to be what of that line? So right there. So the slope is 2, and that's making sense. So count that off and just double check that. Other things we can look at for this is we can look at, well, calculate what negative 2, 4 would be. So if you do that calculation, you'll see that it's 0. So here's negative 2, and it's off the charts, it's way up. It's way up here, so I can't really draw it very well. But basically what you're going to get then is a horizontal tangent. So you're going to get this horizontal tangent when you look at negative 2, 4. So check that out. And which would make sense because you end up getting a slope of 0. Okay, so it's horizontal. Okay, so double check both that. Spend a little more time working through that question. I went kind of fast and counted problems off more than I really wanted to. It didn't say graph this. Actually, all it did was say find the average rate of change. But that's what we're going to be doing. We're going to be figuring out the vertex in a better way, the max and mins, and all that kind of stuff.